You're welcome to day 16 of 50 days of tutelage. And if you've been following so far, we've learned so many things in math, in physics, and chemistry. So if you are lagging behind in any of these things, you can check the playlist for the classes that you have missed already. And before we get into the class, don't forget to get your notes and your writing materials. Now, today in mathematics class, we'll be talking about ratio, proportion, and variation. These guys might sound like they are very simple and trivial, but the thing is that in science generally, in chemistry, in physics, in biology, and even social sciences, we use these three guys a lot, and they are going to be a building block of so many things that we're going to be doing. So, what is ratio, what is proportion and variation, and how do they apply to these different field of sciences? Let's start with ratio. Ratio can be coined from the word rate. Rate. And what is rate? Rate is simply a quantitative comparison of two or more numbers. That is, you want to compare the value of two or more numbers. You're trying to compare them together, quantitatively, of course. Now, this definitely indicates how many times a value relates to another. So if you have a value A, so like I said, it can be two or more. So A ratio B, you are looking at how many times if the value A relates with value B. So you're trying to compare their size together. Okay, in what way is B bigger than A? Or in what way is B smaller than A? In terms of value, I mean quantity generally. And then this can extend to even three numbers, three values, three entities. So you can have something like A ratio B ratio C. But in the two, picking two things to find their ratio together, we can also interpret this as a form of fraction. You can interpret this as a form of fraction, A ratio B. However, the misconception that you might have is that we have what we call equivalence ratio. For instance, 1 ratio 2 equivalent to 3 ratio 6, because you can simplify them into this. But one of the things you need to be very, very careful with is that whenever you are doing anything that involves ratio, you need to properly annotate and use the rate that you have been given. Because if you're given 1 ratio 2 and you decide to manipulate your way around and use 3 ratio 6, sometimes it might lead you into trouble. So it is better that you stick with 1 ratio 2 that you are dealing with than you use 3 ratio 6. In fact, what we like to do instead is that we like to go from ratios like this, complex ratio like this, to simpler ratio. We like to simplify them such that, so ratio is best represented when none of those rates, none of those quantities can actually reduce each other. For example, if you have 1 ratio 3 ratio 4, this is perfect. But compared to when you have 2 ratio 6 ratio 10, now this can be simplified further into 1 ratio 3 ratio 5. So this ratio, they are what? They are called equivalent ratios. Equivalent ratios. So I've explained that rate can also be written as what? As a form of division, and then you can always do this. Now, how do we now share ratio? So to share ratio, we always have what we call total ratio. So total ratio. So what's the total ratio of, let's say for instance, now 1, 3, and 5. Total ratio will be 1 plus 3 plus 5, and that is going to be 9. So this helps us to be able to get what portion belongs to 1, what portion belongs to 3, and what portion belongs to 5. So in the case where we are sharing something like, let's say, 81 81,000 US dollars, we're sharing 81,000 US dollars. So you want to know what will be the share of the person whose ratio is 1, what will be the share of the person whose ratio is 3, and what will be the share of the person whose ratio is 5. Now you can see that one of the mistakes you can make here is, for instance, I said 1 plus 3 plus 5 is the total ratio. If I'm not careful, I can go ahead and say, oh, the ratio of this is 2, so I'm going to say 2 over total ratio, which is 9. I've already misplaced them for each other like that. If I'm using the ratio 2, 6, and 10, then I should take the total with 2, 6, and 10, which will be 2 plus 6, that is 8, 8 plus 10, that is what? 18. So I should not be mixing them up together. So the correct thing is either 2 over 18 or 1 over 9. So any of those two will work. But when I'm beginning to misplace them for each other, so in exams, most students, they get all pumped up and they get carried away and they make such mistakes. So watch out for that. So you just multiply this fraction with the 81, and then you're going to get the share for the person with ratio 1. And you do that for other ones as well. Now, like I said, we have equivalence ratio, and I think I've explained that already. In the next one, which is proportion. What is proportion? Proportion is actually about comparing two things together. Either they are directly proportional or they are inversely proportional. It is also related to ratio, because when you're comparing these two things together, you can always find their ratio and you get a value. This value that you would get is going to give you a form of a constant. So the difference in this case is that when we're dealing with proportion, we are saying that A is proportional to B. So that implies that A is varying. A is a variable. If you see, I'm already talking about variation like that. So A is a variable, and then A as a variable, it is in proportion with B. So that implies that I can write A as a constant multiplied by B. So if B is 2, then A is 4. So what I can imply from here is that 4 will be equal to K multiplied by 2. That implies that K is equal to 2. So at every point in time, I can rewrite this and say A equals 2B. So you can see the proportion now. A equals what? 2B. And if I divide A and B equals 2. So the ratio A and B is always going to be what? 2. The ratio A and B is always going to be what? 2. So if I ask you to pick any A and B that will satisfy this condition, then you can begin to look for A. A can be 6 and B will be 3. A can be 10 and B will be 5. So you can see that they are proportional to each other. So we have the direct proportionality and we have the inverse proportionality. So I've talked about direct proportionality here. Direct proportionality is when whatever happens to B is the same thing as what happens to A. And from there, like I said, you can have a constant K, which relates both of them together. So if B increases, A also will increase. If B decreases, A also would decrease. So the same thing that happens to B is what happens to A. And with this constant of proportionality, you can say that A, like I said already, A over B equals K. What is K? K is a constant. And like I've already explained, that implies that no matter what combination of A and B that you pick, their ratio will always give the same result. So you can say something like, if I pick A1, B1. If I pick any other A, which is A2, and I pick B2, if I pick any other A3 and B3, these guys will always be equal to the constant K. That is what it means. The ratio of A and B will always be constant. Why? Because they are directly proportional to each other. The next one is the inverse proportionality. What is inverse proportionality? It simply tells us that the reverse of whatever happens to one is what happens to the other. So if A is proportional to the inverse of B, then we call this one inverse proportionality. This is what? Inverse proportionality. So what this simply means is that if B should decrease, A will increase. If B should increase, A will decrease. And here as well, you can introduce a constant of proportionality. Let me call this one K2. So K2 over B. And in this place, what you have is what? AB equals K2. As you can see here, we do not have a ratio. Instead, we have a product of two things, which is constant. And if you apply the same thing I explained earlier, that implies that for any A and B, any combination of A and B that I pick, and I find their product together, they will always give the same result, which is still what? K2. And that is for direct and inverse proportionality. So take note, for direct proportionality, their ratio is always going to be constant. For inverse proportionality, their product is always going to be constant. And that is for what? direct, and inverse. But we also have what we call joint. We have what we call the joint variation. Now, joint variation is such that you are combining not just one together, you're combining two of these things together. So joint variation always involve when you combine multiple variables. At least you have minimum of three. You can see that in this case, I've combined two variables in the inverse proportionality. I've combined two variables in the direct proportionality. But when we deal with joint proportionality, we oftentimes always combine at least three variables in this case. So, for example, you can say that y is varies directly as x and inversely as y. Y varies directly as x and inversely as y. So in this situation, oh, that's a slip of tongue. I meant to say z. It varies directly as x and inversely as z. So what you do here is that you introduce a constant of proportionality. So y is going to be equal to k. Y is going to be equal to k. Then you have x at the top and you have z below. So this means that y is being affected by two things: an increase in x, an increase in z. Increase in x will cause an increase in y, but increase in z will cause a decrease in y. And so it depends on which one does more of the increase, or which one that will determine how this is affected. So if x increases greatly, then y overall will increase greatly as well. But if z is the one that increase greatly, even though x is also increasing, then y overall will actually decrease. So z is inverse, x is direct, but we have the two things together at once, and that is what we call joint variation. So in this case, with this constant of proportionality, you can make it the subject. So y equals kx divided by z. So if you isolate k in this place, that implies that yz over x equals k. So similarly, you can say that y1 z1 divided by x1 equals y2 z2 divided by x2. This, for any arbitrary y, z, and x that you pick, their ratio in this manner will always be equal to the constant k. And the last one is partial variation. Partial variation. Now, for partial variation, in this situation, we always have two constants. So when you introduce two constants into the whole system, this is where you have a form of partly constant and partly varies and all of that. So for instance, if I give you an expression, so you have y equals kx plus c. So what you notice is that the two things that are variable here, this k and x are the variable 1, variable 2. K is a constant and c is also a constant. So the presence of two constants together is where we have partial variation. So I'm going to limit this class to this particular point. If you want to see videos of solving problems, difficult problems on this particular topic, just subscribe to my channel and then you'll get notified when I'm solving those problems. But I want to quickly show you how this thing applies in physics, in chemistry, and the likes. So for instance, there are times that you're working a physics problem and they had given you a question. Let's say they had given you a question about the simple pendulum. And then the simple pendulum has a period of 2 pi square root of L over G. So if the simple pendulum has a period that is this, 2 pi square root of L over G, then you want to determine what is one thing when another thing is this. This only have period and length. I should have picked something that has more variable. Anyways, I'm going to use this regardless. So how can we apply this as a ratio thing, or how can we apply this as a proportion thing? What you notice here is that in physics, generally, of course, 2 is a constant, pi is a constant. The two are known numbers. But generally, with regard to g as a constant as well, that is acceleration due to gravity. So what we do is that we can isolate them actually, such that we can say t equals 2 pi multiplied by square root of L multiplied divided by square root of G. Under SOD, I'd already explained to you that you can have square root of L divided by square root of G. It is the same thing as square root of L over G, provided that G is not equal to 0. And you can go further by saying that this is 2 pi divided by square root of G multiplied by square root of L. So all I've done is that this guy at the denominator here, it can actually be under this thing and it will still be the same thing. You cannot distribute it. It is multiplication that is in between them. It is not addition. If it was addition, that is when, and then this root of g is outside, then you distribute. But in this case, you can actually just zone the denominator to one of the numerators. It will still work. But once you are zoning it to one of the numerators, it leaves the other one completely. So now we have this. This entire thing, 2 is a number, a known constant. Pi is also a known constant. And g in physics is also a known constant. So that implies that I can say all of these together is a big K, a big constant. So you have an expression of this nature. T equals a constant multiplied by the square root of L. Square root of L. And this implies that the ratio of T square root of L is always going to be constant. That is why you would have seen that T1 over square root of L1 equals what? T2 over square root of L2. And what you notice here is that T varies directly as the root of the length of a simple pendulum, T being the period. So this is one of the ways you apply such concept. I know you would have seen this rule before. P1 V1 over T1 equals P2 V2 over T2. This is from your chemistry, where you have this combination. This is pressure, this is volume, and this is temperature. So according to the general equation, PV equals nRT. So the general gas equation, PV equals to what? nRT. So N is going to be constant. R is also going to be constant. So in that situation, PV and T are the variables. So you then have PV divided by T equals nR. So since these two are constant, then we have P1 V1 over T1 equals P2 V2 over T2. And that's it for today. I'm going to see you in the next one.